continental collision and crustal thickening are how Earth builds its highest mountain ranges and widest plateaus. When buoyant continental blocks converge, subduction of dense oceanic lithosphere ends and the continents collide. Instead of one plate diving deep, the crust shortens, thickens, and piles up, creating towering ranges with deep crustal roots. We begin with two continents separated by an ocean. Dense oceanic lithosphere subducts beneath one margin. As convergence continues, the ocean is consumed and the buoyant continents come into contact, triggering collision. At collision, subduction of buoyant continental crust is resisted. The former ocean is welded shut along a suture zone that can contain ophiolite fragments, pieces of ancient oceanic lithosphere. Massive thrust faults stack slices of crust into a fold and thrust belt. The crust thickens dramatically and grows a deep root that supports the high mountains by isostasy. In active collisional cores, crustal thickness can exceed 70 to 80 kilometers, compared to about 35 kilometers for average continents. A deep mountain root of dense lower crust and lithospheric mantle compensates the topography by isostasy. A rule of thumb: to support about 5 kilometers of elevation, you need a root roughly 30 kilometers deep. Collisional belts show distinct zones from the suture outward. Closest is the suture zone with ophiolites. Flanking it are metamorphic cores of high-grade rocks. In the Himalaya, a high-grade core is bounded below by a major thrust and above by a low-angle normal fault and extensional detachment that together helped extrude hot mid-crust. Outboard, fold, and thrust belts propagate into the foreland over time. In many collisions, lower crust from the indenter underthrusts far beneath the plateau, building the lower part of the crustal root. Above, a wide, high plateau develops behind the main range. Thickened crust is buried to great depths, heats up, and undergoes high-grade metamorphism. Partial melting of the hot, mid-crust can form leucogranite bodies that intrude the core. These processes peak tens of millions of years after initial collision. Once mountains rise, erosion becomes intense, especially where climate delivers heavy rain. Erosion removes mass and helps the deep crust rise by isostatic rebound. Meanwhile, very thick crust may fail and extend under its own weight, forming low-angle normal faults that help exhume the hot core even as thrusting continues elsewhere. Collisions are three-dimensional. Some crust escapes sideways along large strike-slip faults, a process called lateral extrusion. This helps accommodate convergence without all the shortening becoming vertical thickening. Examples: the Tibetan Plateau has crust thicker than 70 kilometers over broad areas, and local zones approach 80. The Alps reach about 50 to 58 kilometers beneath their highest peaks, roughly double the typical European crust. To summarize, 1. Continental crust is too buoyant to subduct deeply, so collision causes shortening and dramatic thickening. 2. Thrust systems and fold and thrust belts stack the crust, building high ranges with deep roots supported by isostasy. 3. Thickened crust undergoes metamorphism, melting, extension, and erosion, often forming wide plateaus that also spread laterally. These processes together build and shape alpine, Himalayan-type orogens.